Hi students, so now here we are going to learn about another new very interesting topic. It is called as the cyclic codes, okay? And this is the cyclic code. Once you have understood what's a linear block code, then understanding cyclic code will not take much time. It's a very simple topic, all right? So this code, a binary code, is said to be cyclic if it satisfies the following properties. And the first property is, we already know, it is the linearity property. We all know what is linearity property, right? We have seen it in the previous videos. That is, the sum of two code words is also a code word. That is the linearity property. If you take any two valid code words, okay, when we talk about sum, I meant the XOR function or the modular to sum. So if I take the sum of any two code words, okay, if I take the sum of any two code words, then that code word, that sum, is also one of the code word. That is why it's called as the linearity property. Okay, now let's look at the other property. The other property is called as the cyclic property. Now this property is a new property, and it says that any lateral shift of a code, when we talk about lateral shift, I meant it's a cyclic shift. Any lateral shift of a code word is also a code word. This is the one of the new additional property to cyclic code. So basically, in other words, a cyclic code is actually a linear block code which also has a cyclic properties. Now, what do you mean by the second property, cyclic property? What is the meaning of that? Let me just give you a very simple way of explaining this. For this, you see, let V, okay, as usual, we always take the letter V, right? Let V be the code word of n bit. Okay, V is a code word of n bit. Okay, V is a code word of n bit. So that means V is having n bits. I'm going to represent V like this. That is, V is equal to, okay, and the bits I'm going to represent it as V0, V1, V2, V3 up to Vn minus 1. This is how I'm going to represent the code word V. V0, V1, V2. Remember, this V0, V1, V2, these are the bits. So therefore, these values can either be 0 or 1. Okay, all these values can either be a combination of zeros and ones. Okay, so this is how you represent the output code word V. Okay, in your previous chapter, you used V representing as V1, V2, V3 up to Vn. But here, instead of that, I am going to represent using V0. Since it's starting with V0 and since it is n bit, it should end with n minus 1. That is why it's called as from V0 to Vn minus 1. This is how I'm going to represent the code word V. Okay, you'll understand why I'm representing this in the coming time. I will tell you why we are representing this code word in this format. Okay, so if this is a code, according to the cyclic code, if this is a code word, if this is a valid code word, then V of 1, where V of 1 is another code word and it is represented as Vn minus 1, V0, V1, V2, V3, up to, and the last code bit over here is Vn minus 2. So if this is a code word, then this is also a valid code word. That is the meaning of the cyclic codes, the set of all these cyclic codes. If you look over here, what is the difference between this and this? This code word is actually the cyclic shift of this code word. That is, if you shift this code word to the right, every bit moves to the right. That is, V0 will come over here, V1 will be shifted over here, V2 will be shifted over here, V3 will be shifted over here. Like that, every bit will be shifted towards the right, and the rightmost bit becomes the first bit. It comes and goes to the leftmost side. It becomes the first bit. This is what you call as the cyclic shift. So a cyclic code is a set of code words in which the code words are not only having the linearity property, but also they have the cyclic property. That is, you can find the value of one code word by shifting the value of another code word. Just shift towards the right. It's this, in this example, I'm implementing this by shifting it towards the right. So if you shift towards the right, what happens? The last bit, the rightmost bit, becomes the first bit, and all other bits will be shifted to the right. That's all. This is the meaning of cyclic code. It's very simple, okay, very simple. So in that case, if v of 1 is a code, it's a valid code word, then what about v of 2? V of 2 is also another valid code word, and v of 2 means nothing but the cyclic shift of v of 1, which is, in that case, the first value will be v of n minus 2, comma, v of n minus 1, comma, v0, comma, v1, comma, v2, comma, and it goes on and up to v of n minus 3. See, so what is v of 2? V of 2 is a cyclic, is a code word which is got by shifting v of 1 by one time. Or we can also say that v of 2 is a cyclic code word which is shifted when v is shifted two times. So we can either say when v of 1 is shifted one time, we'll get v of 2, or we can also say that if we shift v two times, we'll also get v of 2. So v of 2, like that, we can define v of 2 in two ways, you see, either by shifting one time by this or shifting two times by this. So that is why. So here what happens is the same procedure, that is the last bit becomes the first bit, and all of the bits are being shifted to the right. Okay, in the same way, what is v of 3? V of 3 means shifted three times. This code word has been shifted three times to the right. So in that case, you will get, it starts with v of n minus 3, v of n minus 2, v of n minus 1, comma, v0, comma, v1, comma, v2, v3, v4, and goes on up to, and the last bit will be v of n minus 4. So this power of v that you see here represents the how many times it has been shifted with respect to the original code word. That is what this means. So in that case, so if v of 1 is shifted by one time, v of 2 is shifted by two times, v of 3 is shifted by three times. So if I say v of I, where I is an integer shifted by I times, in that case I can represent this as v of n minus I, comma, v of n minus I plus 1, comma, v of n minus I plus 2, comma, and it goes on, and it starts with v0, v1, and it goes on, and the last bit will be v of n minus I minus 1. This is how, this is the set of cyclic code words. These are the set of cyclic code words. That is, these code words not only have the linearity property, but also they have the cyclic property. That is, if we cyclically shift one bit to the right, then that becomes a new code word. Okay. So therefore, like that, we can get a set of code words like that, valid code words like that. That's all. This is very simple. This is the meaning of this word cyclic codes. Okay. So one important advantage of this cyclic code, which is not there in the linear block code, one of the main advantages that these cyclic codes can be expressed by code polynomials. We can express the cyclic codes by what you call as the code polynomial as a function of a variable called x, as a function of x. This is one of the most interesting advantage of cyclic codes, which is not there in the linear block code. That is, we can express each code word that you're seeing here in terms of its polynomial. And what is the advantage of using that polynomial is that it becomes easy for us to do different kinds of operations like multiplication or division or any of these factors, any of these operations using code polynomials. That is, we are basically expressing each of these code words in terms of code polynomial. For example, okay, let me write the code word of v again. Okay, so v, I am expressing v. We all know that v is equal to, is a code word, bits is given by v0, v1, v2, and it goes on up to vn minus 2, comma, vn minus 1. Okay, so let this be the code word. So if this is the code word, then capital letter v of x, where v of x is the code polynomial of the code word v. Okay, so v is basically a code word, and v of x is the code polynomial of v, and v of x is given by v0 plus v1 into x plus v2 into x square plus v3 into x cube plus, and it goes on. And the second last term, v of n minus 2 x raised to n minus 2 plus, and the last one is vn minus 1. So vn minus 1 x raised to n minus 1, which means, this means that v is actually a code word of n bit. And if v is a code word of n bit, then its polynomial is of degree n minus 1. That is a code word of n bit. Okay, or any letter, let it be any number. Okay, it can n or k or whatever it is. A code word of n bit has its polynomial of degree n minus 1. An n-bit code word has an n minus 1 degree polynomial. That is what this means. So if you look over here, that is why, now you all understood why I have started over here with v0 and ended with vn minus 1. So that it will be easy for you to write the code polynomial. That is why. That is why I have written in this format. So therefore, v of x is a polynomial of degree n minus 1. Okay, and that's represented as v0 into plus v1 of x plus v2 of x. The first bit, the first bit is multiplied with x raised to 0. The second bit v1 is multiplied with x raised to 1. The third bit is multiplied with x raised to 2. The fourth bit is multiplied with x raised to 3, and goes on. And therefore, the last bit is multiplied with x raised to n minus 1. That is why this is called as the code polynomial of degree n minus 1. Okay, so this is why. So an n-bit code word has a n minus 1 degree polynomial, and it's represented like this. So x is the variable. That is why they are calling it as a function of x, v of x, because x is the variable over here. Okay. And the value of, as usual, the value of v0, v1 can either be a 0 or it can either be 1. That is, v0, v1, v2 are nothing but binary numbers. Okay, binary values. All right. So this is v of x. So if this is v of x, then in the same way, we all know what is v of 1, right? V of 1 is the cyclic shift of v. So therefore, v of 1 means we shift the code word v one time. So we'll get v of n minus 1, comma v0, comma v1, comma v2 up to vn minus 3, comma vn minus 2, right? So this is how the code would be when you be shifted by one time towards right. So this is the code word. So what is the polynomial of this? What is the code polynomial of this? The code polynomial of this is given by capital letter V of 1 of x. V of 1 of x. Capital, just like how you wrote capital letter V of x, this is V of 1 of x, to represent that this is the code polynomial of V of 1. And therefore, just like how I wrote V of x in terms of V, I can write V1 of 1 of x, V of 1 of x as in terms of V of 1 by this equation, that is Vn minus 1 plus V0 into x plus V1 into x square plus V2 into x cube plus, and it goes on. In that case, Vn minus 3 into x raised to n minus 2 plus Vn minus 2 into x raised to n minus 1. This is how we represent the code polynomial of the code word of V of 1. Same, just like how I represented this in terms of this, I represented this in terms of this. That's all. So if you look over here, this is also a code word of degree n minus 1. Why is this a code word degree n minus 1? Because the number of bits over here is also n. So that is what is the most important thing you need to understand. If a code word is having n bit, then if you are going to convert it to its polynomial, then its degree must be n minus 1. Okay, it should always be n minus 1. That's why you can see over here the highest degree over here, the highest power of x over here is n minus 1. So therefore n minus 1 is the degree of this polynomial. Likewise over here also, here this is of n bit and the highest power of here is n minus 1. Therefore the degree of this polynomial is n minus 1. So this is how we wrote. Now what I'm going to tell you one more thing. This is very simple, right? So one more thing I'm going to tell you is, how did I write this? I wrote this by looking at the code word. Likewise, I wrote this by looking at the code word. So like this, I can write the code polynomial of any cyclic code word. I can write the code polynomial, right? Because all I have to do is multiply the first bit with x raised to 0, which is 1 itself, multiply the second bit with x, multiply the third bit with x square, multiply the fourth bit with x cube, and it goes on. That's how I got this code word, and that's how I got this code word. Okay, so now I'm asking you, how can we find the code polynomial from the other code polynomial? That is what you need to understand, how to find the code polynomial looking from other code polynomial. Instead of looking at the code word, okay, instead of looking at the code word, how to find the code polynomial from another polynomial. That is what I'm going to do. So just to make you understand that, what I'm going to do is, I'm going to write these two equations again, just so that we can understand the similarity between them. Okay, so this is v of x, right? This is v of x is equal to v0 plus v1 of x plus v2 of x square plus v3 of x cube plus, and it goes on, plus vn minus 2 x raised to n minus 2 plus vn minus 1 x raised to n minus 1. Now if I look over here, this is the cyclic shift of this code polynomial, that is v of 1 of x. Okay, I'm going to write this again. This is vn minus 1 plus v0 into x plus v1 into x square plus v2 into x cube plus, and it goes on, plus vn minus 3 into x raised to n minus 2 plus vn minus 2 x raised to n minus 1. Okay, so how to derive this code word from here, that is what I'm going to tell you right now. Okay, and how to do that is, if you compare these two code, okay, if you just simply compare these two code, you can see that here v0's alone, right, v0's alone, but here v0 is multiplied by x, here v1 into x, but here it is v1 x square, here it is v2 x square, but here it is v2 x cube, which means every terms over here is multiplied by a single x, right? Every term over here is multiplied by a single x. So what I will do is, I will do that step. Okay, I'm going to multiply v of x into x. Let us see what will happen if I do that. So I'm going to multiply x into v of x. Okay, so what will I get if I multiply this? I will get v0 into x plus v1 into x square plus v2 into x square into x is x cube plus v3 into x raised to 4, and it goes on, and you will get over here as vn minus 2 x raised to n minus 1 plus vn minus 1 x raised to n. So if you look now, if you compare, so what I did is, I basically multiply, since why I multiply this x is because this v0 is multiplied with into x. With just when you compare over here, right, one x is missing over here. Likewise, when you compare this with this, one x is missing. When you compare this with this, one x is missing. So because of that, what I did is, that's a first step. Okay, to understand how to get this, I multiplied v of x with x, and I got this function. And when you compare this one, this polynomial with this polynomial, you can see that every term is same, right? Every term is the same. Every term becomes the same. You see over here also, this term comes before this. Okay, so every term is the same except the last term. The last term over here is vn minus 1 x raised to n, whereas over here it is only vn minus 1. So this is the only difference. So here we have vn minus 1, but here we have vn minus 1 x raised to n, which means all I need to do is simply, after this, all I need to do is simply substitute x raised to n equal to 1. That's all. So what will happen if I substitute x raised to n equal to 1? Then this will become 1. So if this becomes 1, then this will become only v n minus 1, which is the same. Then in that case, then these two equations will become simple. These two equations will become equal, right? All I have to do is multiply v of x with x and then substitute x raised to n equal to 1. Okay, so what will happen if I substitute x raised to n equal to 1? I will get vn minus 1 plus v0x plus v1x square plus v2x cube plus everything will be the same, and the last term will be vn minus 2 x raised to n minus 1. You see, the reason is because I substituted this x raised to n equal to 1. Okay, and since this term does not have any x anymore, so what I'll do, I'll just write it, I'll just rearrange it and put it as the first term, as the just to show in the increasing or power of x. Okay, so now if you compare these two equations, they are the one and the same. So how did I get this equation? I multiplied v of x with x and then I substituted x raised to n equal to 1. So now you will ask me, can I simply do this? Is it possible? Theoretically, it is possible. And if you ask me why theoretically it's possible, is because I already told you that a code word of n bit has a polynomial of degree n minus 1. It should have a degree of n minus 1. If I had multiplied v of x with x, see what happened. When I multiplied v of x with x, I got a polynomial, alright, but its degree is wrong. Its degree is greater, its degree is n. A code word of n bit should have a polynomial of degree n minus 1. But here, the degree of this polynomial is not n minus 1, it is n. It is supposed to be n minus 1. That is why I substituted x raised to n as equal to 1. So by substituting the x raised to n is equal to 1, I removed this x over here and I made this term as the first term. So in that case, I got these two polynomials as one and the same. This process, what I just said, is what you called as the multiplication modulo x raised to n plus 1. That is the name of this process. Multiplication modulo x raised to n plus 1. That's the name of this process. That is, what I did is I multiplied v of x with x and then I substituted substituted x raised to n is equal to 1. And in that way I got this polynomial from the previous polynomial. Okay, so like that I can get the cyclic shift version of the previous polynomial if I follow this step. Okay, so like this is how we write it. So now this is very easy to understand and you can apply this theorem anywhere. So now you don't have to write this code word every now and then. Okay, because that will take a lot of time writing the code word and then looking at it and then writing the polynomial. What is much more better is writing the polynomial from here, from the previous polynomial, and then substituting x raised to n as equal to 1. That's all you need to do over here. Okay, but the one thing is that this is all very well and good. It's very easy to explain all this in terms of theory, but how do you actually implement this kind of an operation mathematically? See, because mathematically you cannot simply substitute any value as you wish as equal to 1 or anything like that. So how do you do this in terms of mathematical operations? How can you describe the same process, or how can you describe this process mathematically? Okay, multiplication modulo. If you all remember, some of you who are very good at maths, you all know what is the meaning of modulo, right? Modulo actually means remainder. Right, it actually means remainder. So how do you express the same operation mathematically? That is how I'm going to tell you right now. You can consider this as the second approach or second method of getting v1 of x from v of x. Okay, and that approach is, again, what you're going to do is, it's very simple. I will just explain this process one more time. That is, here I'm going to take my my v of x. Okay, I'm going to take my v of x over here, and I'm going to multiply with x of v of x, right, over here. So let me see what we can do over here, what magic we can do over here. All right, so let me write this equation one more time. X v of x, okay, this is the interesting part. X v of x is equal to v0x plus v1x square plus v2x cube plus, and it goes on, plus vn minus 3 vn minus 2x raised vn minus 2x raised to n minus 1 plus vn minus 1 x raised to n. Okay, right? And also, and again let me write the equation for the other one also, that is v1 of x, okay, is equal to vn minus 1 plus v0x plus v1x square plus v2x cube plus, and it goes on up to vn minus 2 x raised to n minus 1. Okay, so I'm going to explain the same process, but this time I'm not going to substitute x raised to n equal to 1. Okay, that is a theoretical way or a shortcut way of writing the polynomial. So now I'm going to express the same equation, that is I want to find I want to express v1 of x, or I want to derive v1 of x from v of x. Okay, and as usual the same procedure is I multiplied v of x with x and I got this. Okay, I'm not going to write v of x again, but instead I'm going to just write I'm going to multiply v of x with x and I got this equation. Okay, and now I'm going to derive this from here. So how I'm going to derive this is, you see, if you compare this whole thing, if you compare this equation with this equation, see, from here to here everything is the same, right? From here to here everything is the same. Likewise over here also, from here to here and from here to here everything is the same except this term, right? If you remove the first term from here and if you remove the last term from here, the rest of them are exactly the same, right? The rest of the terms are exactly the same. That is, here from the first term to the second last term, and here from the second term to the last term is the same for each other. Okay, I just want you all to see that. So what I'm going to do is, we all know what is 0 plus 0, right? We all know what is 0 plus 0. 0 plus 0 is 0. We all know what is 0. We all know what is 1 plus 1. 1 plus 1 is also 0, because this plus that you see here is actually the XOR function or the modular 2 sum. That is, 0 plus 0 is 0. 1 plus 1 is also 0. In that case, vn minus 1 plus v of n minus 1. What is vn minus 1 plus v of n minus 1? That is, same two terms are being added together. You will get 0, right? You will also get 0. So what I'm going to do is, I'm going to put this vn minus 1 plus v minus 1 over here. So what will I get if I do that? I will get x, v of x is equal to v0 into x plus v1x square plus v2x cube plus, it goes on up to vn minus 2 x raised to n minus 1 plus vn minus 1 x raised to n plus vn minus 1 plus vn minus 1. Okay, I'm going to write, because this is actually plus 0, but 0 can also be represented like this. So I write in vn plus vn minus 1 plus vn minus 1. Okay, so this is how I express the polynomial. Okay, then what I'm going to do is, okay, here the first term is vn minus 1. So what I will do is, I will take one v of n minus 1 and I will put it over here. So I will get vn minus 1 plus v0x plus v1x square plus v2x cube plus, I forgot to put dots over here. Okay, it's supposed to, okay, plus, and it goes on, and you will get vn minus 2 x raised to n minus 1 plus, okay, so what I did is I took one Vn minus 1 and I put it over here, and I'll get the remaining, so remaining term will be Vn minus 1 x raised to n plus Vn minus 1. I'll take Vn minus 1 common, so I will get Vn minus 1 into x raised to n plus 1. This is what I will get. You see, this is what I will get over here. That is, what I did over here is that I simply added these two terms extra into the x of v of x into v of x, and I got this, and I moved one v of n minus 1 to the first term, and the remaining I took it as a common. I'll get this equation. Now if you compare this equation with this terms over here, if you compare this entire equation with this term over here, then this is nothing but v1 of x. That is x v of x is equal to v1 of x plus vn minus 1, small letter vn minus 1, x raised to n plus 1. See over here, let me write this equation again. It is x v of x is equal to v of 1 of x plus vn minus 1 x raised to n plus 1. You see over here, that is, from x of v of, I can find v1 of x, this capital letter v1 of x from here by multiplying this, okay, and then plus I'll get an extra term. So that means x v of x contains this term, right? You see, if you look over here, x v of x actually contains this term right here, okay, because from here to here, from the first term to the second last term, it's the same as your v1 of x. So I substitute this entire equation as v1 of x, plus the last term is this extra term will be v of n minus 1. Okay, if you look at this equation, you might have all studied this equation in school. That is, dividend is equal to remainder plus quotient into divisor. You might have all studied this in your school days, right? Dividend is equal to divisor into quotient plus remainder. That's what it's written. Dividend is equal to remainder plus quotient into divisor. And if you look over here, this is the dividend, this is the remainder, and this is the quotient, and this is the divisor. So now I'm telling you how to find v1 of x from x v of x. That is, if you compare this equation, you can see that the polynomial v1 of x is nothing but the remainder of x v of x. It is the remainder of x v of x when divided by x raised to n plus 1. v1 of x is the remainder of x v of x when it is divided by x raised to n plus 1, which means mathematically, that is why this process is actually called as multiplication modulo x raised to n plus 1, which means why? Because we can find v1 of x by simply dividing x v of x with x raised to n plus 1, dividing x v of x into by x raised to n plus 1, and then finding the remainder. That remainder is actually v1 of x. So you can find v1 of x as the remainder. That is, all you have to do is divide x v of x by x raised to n plus 1. Divide them, and the remainder is actually the v1 of x. This is how we actually do the math. This is how we explain the mathematical operation of finding the code polynomial of one cyclic shift from the other code word. Okay, so this is only for one cyclic shift. So if I want to do another extra, if I want to do for an ith cyclic shift, okay, if I do a cyclic shift, if I want to do a cyclic shift of I number of times, I times, okay, in that case, then this equation is written as x raised to I v of x is equal to v of I of x which is the code word you're trying to find, plus q of x is the quotient, corresponding quotient of this q of x into x raised to n plus 1. This is the general equation to find the ith cyclic shift code polynomial. That is, how to find it is, for example, okay, if you want to find v2 of x, okay, for example, if you want to find v2 of x, okay, if you want to find the v2 of x, all you need to do is multiply v of x with x square and divided by x raised to n plus 1 and its remainder. Remainder is v square of x. In the same way, if you want to find the value of v cube of x, that is the cyclic shift code polynomial of the cyclic word that is shifted 3 times. Now, all you need to do is simply multiply v of x with x cube and then divide by x raised to n plus 1, and that remainder, and the remainder of this is v cube of x. This is how we find it. So this is what the simple procedure is. All you have to do is multiply v of x with that corresponding power of x, and the number of times you want to shift it, you multiply that with its corresponding power of x, divide by x raised to n plus 1, and its remainder will give you the corresponding polynomial of the shifted cyclic code word. So this is how we introduce the cyclic code.